What's going on? I'm regrettably a bit sick today. I knew a lot of people have been getting sick, and I was really on top of my hand sanitizing and my not touching my face, but my efforts weren't enough. So I don't feel too bad. Like I'm not particularly compelled to just sit in my bed all day doing nothing. But I also don't feel like going outside. I mean, not only do I not feel like it, but I'm not trying to not trying to do unto others as I've been done onto type. Not necessarily, but anyways, yeah. I'm gonna just stay inside and do something kind of low effort for about 8 hours. And what better thing to do that than one tapping a book on static program analysis? I've been meaning to read, actually, I already began to read. I think I've read the first 3 chapters of this through type analysis. Though not as recently as December 16th, so it seems like it's gotten updated, which is kind of cool. But yeah, we got some food in the kitchen right quick. But yeah, we're gonna try to one tap this. I'm really looking forward to this book. Actually, I was recommended this book by my compilers professor before I was even in his class. I was just like, "What's a good book on compilers or programming languages?" Because I mentioned I was starting to read the Dragon compilers book, and it ends up that this is curious. And so we're gonna one tap it. Might take more than 8 hours because the last 210 page the rest book I read in this page range was not as interactive. But all right, we'll see when we get my food. Probably watch something on YouTube and then start reading this.
About half a year ago, I posted a video where I tried computing really
I've
large
been wanting to watch
Fibonacci
this.
numbers, and my language of choice was C++. By the end, I surpassed the 4 millionth Fibonacci number in just under a second. The video was, to my surprise, very well received. Nonetheless,
Okay, first off, I had no idea. Second off, I don't have the extension on here. It's Firefox.
about half a year ago, I posted a video where I tried computing really large Fibonacci numbers, and my language of choice was C++. By the end, I surpassed the 4 millionth Fibonacci number in just under a second. The video was, to my surprise, very well received. Nonetheless, there was a noticeable population of commenters who took the video as a challenge and proceeded to decimate my meager 4 million in a variety of languages. These commenters were quite respectful and sportsmanlike, despite rendering my 30-minute monologue completely moot. That being said, I thought to myself, if it's so easy for everyone to beat me, who's to say I can't beat me as well? After careful consideration, I decided to play the optimization game again, but this time I was going to do it in C. And off I went, laying the groundwork for this endeavor and announcing it in a video with a not at all clickbaity title. And boy, did that ever open Pandora's box. You could say that the last video inspired a handful of passionate responses. Some people were really gunning for my self-esteem, trying to make me feel stupid for how I massacred their favorite programming language. Unfortunately for them, I'm a mathematician. I always feel stupid. That being said, if you really want to leave a deep cut in someone's self-esteem, follow the show don't tell rule. For example, instead of saying, wow, this guy can't be bothered to learn proper C++ move semantics and thinks switching to C is going to magically make things better, try something more like this. Around 8 minutes and 57 seconds in, the C++ Chad claims that the temporary variable is moved into B because its value is no longer used at that point, but that's completely incorrect. You don't even need GDB or to read assembly to see it. You just need some well-placed debug statements. And then, when you run the program, you'll see immediately that the program is littered with expensive data copies, including the copy of temp into B. It's clear that G didn't do his due diligence and was making baseless guesses about how C++ compiles. For this, G deserves all the vitriol thrown his way. Either way though, the haters are right. My original Fib-Sonichi codebase is fraught with poor performance decisions due to misunderstanding the inner workings of C++. This leads to another important life lesson. You're not a C++ compiler. Well, I really mean I'm not a C++ compiler, but, it's the royal you, so it's all fine. As mentioned in my previous video, I've opted to switch to C in favor of its simplicity, so that what I write has more deliberate effect on the assembly output. Before you ask me why I don't just write assembly directly, ask yourself, do you really think I could make peephole optimizations in x86 better than a mature C compiler? Last time, we left off at the simple linear implementation, which is a quadratic time algorithm that is capable of computing past the 600,000th Fibonacci number in under a second, when I wrote it in C. Next in line is to restructure the naive iteration loop with fast exponentiation. I've already explained the algorithm in the first video, but as a brief overview, remember that the nth Fibonacci number can be computed by taking the nth power of a certain 2x2 matrix. This is beneficial because we can compute the nth power of anything using O of log n multiplications. Even with my poor C++ design decisions, this algorithm takes us past the 800,000th Fibonacci number. But don't be fooled. Just as our linear algorithm isn't actually linear, this fast exponentiation algorithm isn't logarithmic either, thanks to the non-trivial cost of multiplication. For simplicity, I'm just going to work with grade school multiplication for now, which grows quadratically with the number of digits of its factors. We've worked out already that the fast exponentiation algorithm turns out to be quadratic in the index, which we can see by looking at the heights of each of these steps in the runtime plot. These jumps in the runtime happen precisely at powers of 2, since these trigger a new multiplication step in the algorithm. In the C++ implementation, you'll notice that I wrote a general 2x2 matrix multiplication function, but as I mentioned before, there's no reason to be more general than the intended application. In the context of computing Fibonacci numbers, the only matrices we ever see are symmetric, so a general purpose 2x2 matrix multiplication will always do redundant work in this case. In particular, we can instead work with three-dimensional vectors with an interestingly defined product. At a high level, the algorithm looks pretty much the same as we've already seen. However, as I've said in the previous video, the devil's in the details. This is a YouTube video, so I'm not going to go into all the details. You can just read the source code yourself. But let me say a couple of things about it. First, in vector product steps such as this one, I don't update the value of f in place, but rather store the result of the multiplication in a scratch vector and then swap pointers. Secondly, rather than computing 6 products and 3 sums, I compute this vector product in 3 fused steps that are most succinctly summarized by this expression, or this animation. With all of these optimizations in place, can you guess how far we can get? Sheesh! Without even whipping out any advanced algorithms, our fast exponentiation algorithm brings us past the 2 millionth Fibonacci number. For comparison and reference, this is precisely the same order of magnitude as the silver medalist in the original video, which used fast exponentiation of 2x2 matrices coupled with multiplications based on the fast Fourier transform. While this might make you think, wow, C is so much faster than C++, the more correct reaction is actually, wow, G is so much worse at programming in C++. By reducing generality, we reduce the memory requirement of our fast exponentiation algorithm by 25%. If we keep specializing, we can reduce the memory requirements even more. The box product on three-dimensional vectors we defined is just the image of the matrix product on symmetric 2x2 matrices. In particular, it's a sensible product on all three-dimensional vectors. But we're not interested in arbitrary three-dimensional vectors. We're only interested in those vectors whose elements are consecutive Fibonacci terms. In particular, such vectors live in a two-dimensional subspace consisting of vectors whose third component is the sum of the previous two. If we take our box product on three-dimensional vectors and restrict it to this two-dimensional subspace, we get the following stranger-looking product. Breaking this two-dimensional product similarly into 3 fused computation steps, we can see very clear improvements in performance, and our 67% memory footprint brings us up to just over 2 million again. Given our 1 second cutoff, cheap shots at the hidden coefficient in the big O like this isn't going to take us very far, especially since our algorithm takes quadratically larger hits at subsequent powers of 2. The obvious next thing to do would be to simply replace the multiplication algorithm with one of the other fancy algorithms I discussed in the first video, but I don't really feel like doing that right now. Instead, let's flip our fast exponentiation algorithm onto its head. Fast exponentiation takes advantage of the binary representation of an exponent, which it recovers bit by bit starting from the least significant bit. However, we can build the same thing from the top down, starting with the most significant bit and iteratively squaring the Fibonacci vector we're actually interested in, only multiplying the original transition vector at every set bit we encounter. The overall expression is admittedly a lot less pretty when written out like this, but this form of fast exponentiation has some noteworthy advantages, which we can see from the pseudocode. Unlike the original fast exponentiation algorithm, we don't need to iteratively square the transition vector a, which means that our transition steps are much cheaper. In fact, expanding out the box product, we don't even need any multiplications to perform this step. After all, it's just advancing the Fibonacci sequence by 1. Secondly, the only non-trivial box product is a squaring operation, which means that we don't need 2 buffers for arguments and 1 for the result. We can instead get away with just 2 buffers in total. Moreover, our strange box product simplifies quite nicely and naturally breaks into 2 fused steps rather than 3. But gee, you might be saying, this is still a quadratic time algorithm. These are still just cheap shots at the hidden coefficient in the big O. While you're definitely right that this is still an O of n squared algorithm, well, I don't think words are necessary in this case. Hacking away at the constant factor brought us a smidge over the 4 millionth Fibonacci number. Now that our accumulation step for each set bit of the index is effectively just an addition, we no longer have noticeable jumps in the runtime at every power of 2, which also means that incremental improvements are back in business. This simple implementation brings us neck and neck with the gold medalist C++ implementation in our first video. This is exciting for many reasons. For one thing, it's only going to get better from here. We've already explored much more efficient multiplication algorithms, and assuming I don't completely fumble their implementations again, the neuron activation from making big numbers fast is going to be crazy. Already matching my top C++ implementation also brings other good tidings. First, it means C++ is no longer going to be the punchline of my YouTube thumbnails. Secondly, it means that we can finally retire the exhausted jokes about how the YouTuber whose name is partially inspired by the GNU C++ compiler is trash at writing good C++. If you have unsaid jokes in this regard, you'll have to get them out in the comments section now, before the joke becomes irrelevant in later videos. Anyway, if you're still here, thank you for watching. If you liked what you watched, or the implications of what you watched, I believe YouTube has mechanisms in place to express that somehow. If you didn't like what you watched, it's fine. Although I often write code that drags down my reputation, there will always be at least one source of wind beneath my wings.
Let's begin. That sounds kind of cool. Wow. Implementation in Scala of most of the algorithms we cover. Heuristic. Intro. Yeah, I was thinking this. I think about this a lot. Yeah. What's the universal? I didn't get that. I got the first part. I didn't get why it's certain. There must exist some W such as the fail state ST. Yeah. Do I need to know that? I'll still ask GPT just to see, you know. Oh, okay, I didn't know what a total Turing machine was. No algorithm can decide whether a Turing machine that never loops forever might fail on some input. Huh. Failing is like crashing due to a null pointer. Halts and accept, halts and reject, halts and fail, and halt. So given a total Turing machine T, P can decide if T never fails. So it's like the okay. So machine M takes the encoding of some Turing machine T and it'll output S of T. Or construct S of T. Yeah, I don't get it, but let's move on. I don't really think that's the topic of the book in general. You have ints, you have identifiers, expressions, which are ints, identifiers, or infix operators applied to two expressions, or parentheses range expressions, or input. Time to log in. I know you're not supposed to drink caffeine, but All right, what am I doing? All right, I already feel better, bro. Yeah, I was really close to just going to the bed. Nah, bro, not in this economy. So yeah, I didn't understand this. We were defining recursive data types. You replace the A with T with the recursive type mu A dot T. Mu T is a recursive type where T is the type variable waiting for recursive. Hmm. Oh, that's easy. So T is an int T int. So let's try to okay, so recursive list. If I'm at a recursive list, I have list. So first it can just be empty, or it can be a node with data and a list. So if I was doing it here, I do mu, just copy the mu character. So mu t, what's the syntax? Here it is, mu t dot. So it goes here. Mu t dot what? It's a little different because it's not a function. It's not a function. It's of some type. Yeah, this isn't the same. But either way, it'll be t. Could I do like empty or uh, like that? A and B is kind of insinuating like it's some other time type. Yeah, I get it. Я понимаю. All right. So this means this t will be this many times. Cool. And you can have free variables. Type constraints. For each local var, function param, function name, we should use a type variable. Vars x, brackets x. So these are the type constraints of everything. Anything. It's just an int. The only literal is an int literal. So the two must have the same type, which is also the type of the output, which is also an int. Okay. Equality. So that's saying and there. So these are the same and it returns an int. Input. Input is an int. So you can kind of make something. Short XYZ input alloc x. Yeah, what does alloc return? Pointer. That's its own type. Yeah. Dang, that calf is hating me, bro. The general term equality axiom. C T1 to Tn is equal to C prime T1 prime Tn prime Ti is equal to Ti prime. Or implies. Y is pointer to x and y pointer to y. So the equality axiom we have. Okay. Equality relation we have reflexivity. What doesn't have reflexivity? Yeah, okay. Not equal, I mean, okay, sure. Solution assigns a type to each variable so that it's satisfied. A program is correct from a type perspective if there exists a solution. Still a lot left in this chapter. Alright, I think I'm gonna finish this chapter and not want to happen anymore just because I want to work on something else and I have a ton of homework and I can't just spend 8 hours doing something that's not really relevant to anything I'm doing right now. So we're just renaming this to static type analysis. So we have a unification algorithm based on the familiar union find data structure. Okay. So you can kind of union the uses of a particular identifier and find, kind of constrain. That's kind of from more of like a type class perspective though, where you're constraining the set of, or the I list or whatever it is. Yeah, I'm just gonna read the stuff when he goes. From 1964, dude. Bro, how are people coming up with this in 1964? Okay, Fortran was around at that time. Is Commodore 64 referring to bit or year? It's 8-bit. Neither. Okay. Um, 256-bit. Bro. Wow. This freaking letter on this web page is probably taking up more than that. Certainly. Because by the nature of it being in a browser. It's taking up like rendering this letter is probably taking like 3 gigabytes of RAM. We are cooked. Yeah, that's crazy, bro. Bro, how are you caring about types when you have? That's crazy, dude. Yeah, see if make set, fine, and I should probably do some lead. Should consider doing some lead. Some lead. Okay, it's online. It's chill. Awesome. Cool. So you got make set, finds the canonical representative of X by traversing the path to the root. Bruh. Nah, Alani's goated, bro. Before I started popping this. Oh wait. Nah, I was like dying and falling asleep. I was dying, literally hating myself, looking pale as hell, and falling asleep. Now I still look pale as hell, but I'm not dying or falling asleep. Got him. But yeah, you got make set, adds a new node that does initiate its own parents. Yes. Find the canonical representative of X by traversing the path to the root. Union finds the canonical representatives X and Y, makes one the parent name, the other one is the variable. So the end of the data structure largely. Could I implement it? Hell no. I need to make a. Dang, I got so much to learn, dude. In order for you to actually say I'm solid at programming, I really need to pick a language. Probably C++ would be in my best interests. And just implement every data structure, every algorithm, every application, just everything. But seriously, I should be able to know how to just sit down and be able to implement a union find in like 20 minutes. Or just insert any data structure here. Like in any other case, you don't really understand how that works. So I guess I don't understand how it works. See a textbook on data structures. Hmm. Yeah, you should really know how to implement data structures, dude. Like that's just not. That's just lame. You can't implement a data structure. It's just super lame. But okay. Associating a node with each term, the constraint system. For each term t, we invoke make set t. Really? Okay, you give each one its own set. Each term at this point is either a type variable or a proper type, yeah. Mu terms are only produced for representing. Mu terms are only produced for presenting solutions to constraints, as explained below. For each constraint T1 equals T2, we invoke unify, which unifies the two terms if possible and enforces the general term equality axiom by identifying unifying some terms impersonally. Dude, this is why Jiffity is goated. Procedure unify T1 find T1, T2 R find T2. I don't recall the syntax. Oh yeah, I just forgot about the massive freaking aura loss I had yesterday. That was yesterday? That feels like 2 years ago. I was in operating systems class, and the professor was talking about closures and graphs. Yeah, he's talking about closures. And I was actually paying attention too, which is why it's more embarrassing. But he's talking about closures, and he asked if anybody knows what closure is. And I started talking about freaking closure, and he was like, no, in effect. Yeah. Is that how you pronounce this?
Well, hello Internet, and welcome to my Clojure video tutorial. In this one tutorial, I'm going to cover the core syntax of. I'm going to be able to.
I need to start picking up more programming. I guess that is kind of my bane in a sense.
For that side of.
Yeah, I don't really know anything about Clojure.
Hello all, and welcome. Our mutable strings aren't really a Lisp code, and Clojure is no arguments, and we're returning 3, right? That's nice and you solve it with
Yeah, I guess it is a
regular
Lisp
expression. Now you so hopefully this will give us. So that means that if we're filled to
Yeah, I
return
don't
a
really care
lazy
about it. I don't care. Wait. I said I don't care to learn Lisp. How can you not know? How can you not have ever used any Lisp? Like, what? Are you like 10? Awesome. Alright. So yeah, I was gonna like I read this, but I can't say I could teach somebody else this. Teach me this. Alright. So while that's going, I'm gonna hit it. Well, I guess it went rather quickly, but I'm gonna go to the bathroom real quick. And I'll let you watch my Firefox errors. Should be enjoyable. right? So, unification algorithm you're referring to is so for each term, create a node. So I just want to be extra clear here. We also have about an hour until game dev. I didn't realize it was actually in online, which is clutch. Consider this. So x has to be something that then y has to be something. And z is implied from y, implied from x. Okay. Ah, okay. Okay, I think that's chill. Send it back up. Cycle detection. Ooh. Infinite types. So yeah, that's kind of dope. So invokes make set for each term t. For each constraint of the form t1 is equal to t2. Unify, so find the representatives. Yeah, so this is kind of what I was saying. You have this graph of type dependencies. You know that certain operations require certain types, as we saw in the grammar. For instance, all the infix operators require that both of their operands are ints. And then from those rules, you can perhaps anchor the types of certain terms. Yeah, that's kind of dope. And then you can kind of do it by unioning them with their dependencies. You know what I mean? And then eventually you'll get at a more constrained, perhaps literal, or it could be like an input or like the infix operators and such. Yeah, I think I understand that. Okay. A complicated factorial program generates the following constraints. So yeah. And so from, oh yeah, so from these constraints, you have a solution. That's what we're trying to do this whole time. Almost everything's an int. What's not an int is a pointer of an int or a function mapping between various arrays of ints and pointer of ints to ints or pointer of ints. So dope. Recursive types are also required when analyzing tip programs that manipulate data structures. You can imagine a var p, out to null, and a pointer to. Wait. So p is just null. Wait, what is this? Wait, how does that work? Var p. And you're allocating it? No, so p is null. Dereferencing p is p. So now p is a pointer to null. GT. So it's like an infinitely recursive. Rush-hour has an infinite recursive. Skipping exercises as we do. We send the type analysis to programs that use records. So a product type of sorts. Conservatively check whether if not zero is in leading each agent. Distinguished records from other types of values. Yield accesses are only performed on records. Int dot name. Kind of dope. I also like how in Java there's just isn't a thing. Int dot is object. I need a static int factory builder warehouse class immediately. That's the first attempt at type constraint or record construction and field lookup can be expressed as follows, inspired by our treatment of pointers and dereferences. Okay. So we have a set of records. X and E, I'm a bit confused there. These are like, I would consider like an identifier type, yeah. Perhaps the inverse, depending on your syntax. But it has the type. The constraint rule for field lookup says that the type of E must be a record type that constrains a field name X. Okay, yeah. With the same type E.X, yeah. Every record type contains all record fields that exist in the program. Not a special type or any adjectives. Okay. So it's a way, yeah, okay. Okay. Set of all field names. So you have a record with this. What do you call this again? It's like a typeset. do you call that again? Constraints. Type constraint set. Constraint set. What is that called, dude? Constraint set. I'm going to call it a constraint set. Itself. Okay, so that's a bit abstract. So x dot a is equal to empty. Okay. So in effect, you just globally, I don't even know how to say what I'm thinking, but you do what I'm thinking. Yeah. Unfairly rejected. Simple example is this. And so what's the problem with this? X is now a pointer to 17, and it's overwritten with 42. And returning. So what's that problem? Yeah, I don't see it. I thought you could overwrite. Is it because the type of this is technically anchored to be a pointer and now it's an int? Hmm. Ah, because it is not aware that this happened after this. Yeah, that makes sense. I feel like they could have said that. Loki. Polymorphic types. So f of x. Excuse me. F of x just returns a pointer to x, taking in x. Or sorry, the dereference of x. So this must take in pointer to x, yeah. And then f alloc 1 plus the dereference f alloc 2 is the pointer to the pointer 2, which is now the pointer 2. Dereferences 2, f alloc 1. Because it generates constraints. Type of x, the pointer event here. We have a pointer event here. Yeah. For this program, we could analyze the f function first, resulting in the polymorphic type. F of x takes a pointer to x and returns an x. Yeah. Instead, I take the polymorphic type. It's like mu x. Perhaps not even mu x. Yeah, it's not recursive. That's true. Let polymorphism. Oh, I've definitely heard of that. Damas linear style. The price of the increased precision of what polymorphism and type analysis is that the worst case complexity increases from almost linear to exponential. Even without polymorphism, infinitely a good example. Polyrec. So that's a null 1 gx var if x is 0. Where is g? Also, I could just recurse. With functions that are both polymorphic and recursive, type analysis becomes an undecidable general case. This does get really complex very quickly. Like somebody that's been programming for a day can write something to the effect of this. But there is a lot going on. Yeah. I do enjoy these like meta programming-ish things. If you just look at what I've been working on, plugin, programming language, not meta, but si peut dire moi. Giddy up. YOLO. Total requests. So it looks like I had a pull request that contained a like what is that? Smush? Oh my gosh, what do you call that? When you merge and stack, stack and merge. Or what is it? Shrink and merge? Shrink and merge? What do you call that? Where you gotta coalesce all the commits. Squash and merge, yeah. Nah, shout out the other guy that phrased this in the same way as me. So, yet another limitation. Yeah. The pointers, even my compilers class, we just excuse me, we just do not have pointers for the whole class. Escaping stack cell. RP. P's, yeah, we don't have first class functions either because it just makes everything. Once you have function pointers, you're just code. Wait, P is equal to balance. Which makes a var x. Turn the address of x. So this is the null pointer. Yeah. Yet that can be handled by other types of static analysis. All right, so I think all that I just read is what I read. Obviously not very well, because I didn't understand the type thing. Or it has been about 6 months. Dang, I think it's been even more than 6 months. Dude, that's crazy. But anyways, I read it a while ago. And so here is what is really the new content. So we have a chapter here, lattice theory, 14 pages. Whereas the last chapter I wrote was more like 18. So shouldn't take too long. But I think I'm gonna end stream here and perhaps stream something else. I do have a meeting in like 52 minutes. So I might work on my operating system's homework or just do some homeworky thing that's unstreamable. So yeah, I'm gonna end this. Perhaps next time I read this book, we can get into lattice theory, data flow analysis with monotone frameworks and whitening, perhaps. It sounds like a good 2-hour stream. Well, yeah, I'm gonna end it. See you guys.